It's March 1st, 2024. I'm scrolling through the outraged drip feed known as Twitter, or X if you lack a soul, on my phone, and I happen to expand a tweet about some right-wing nonsense going on. Naturally, there's the usual spread of brain-dead blue check replies, and then this one. No premium, just in it for the love of the game. The content here is entirely boring, but the account catches my eye. This tweet was posted by Haruhi Suzumiya. Now, I'm something of a Haruhi fan myself. In fact, at this point, I've been running a club dedicated to translating the Haruhi Suzumiya video games into English for 2.5 years. So seeing my beloved Haruhi say something so asinine lit a spark in me, and a couple hours later, I posted my most liked tweet to date.
You know what? You. Woke's your favorite series in Nintendo DS game.
I realize it's not that many likes, but it's pretty good for me. By the way, he responded to literally every person who replied or QRT'd him except for me, so I think I might have actually struck a nerve. And then he got suspended, so lamau. Okay, but hold on. What even is this video I posted? I mean, obviously, it's a modified version of the renowned hit 2009 Haruhi Suzumiya visual novel Nintendo DS game, Suzumiya Haruhi no Chokuretsu. But how did I manage to make a whole little skit in a couple of hours? How did I even modify the game like that in the first place? To answer these questions in full would require me to make a very long video, and frankly, I don't think I'm up to the task of a 3-hour video essay quite yet. Now, maybe one day I'll make the Chokuretsu magnum opus, but today we're going to be taking a look at the main problem I had to solve in order to make this piece of art. Reverse engineering this game's script files. But before we get into that, we should talk a little bit about the history of the Chokuretsu project. Now, I've already talked about this in a couple of places, most notably in my blog posts on reverse engineering the compression algorithm and archives in this game, but also in the 2 panels I've done. However, today we're not going to be talking about that stuff. Instead, I'll link to it all below. Suffice it to say, after working to translate this game for a little under 2 years, my friend Will and I had an idea. What if we made a full editor for Chokuretsu? Something that allowed people to make their own Haruhi visual novels for the DS. I mean, wouldn't that be neat? It would allow me to put all the reverse engineering work I'd done to use, and it might open the door to a whole new level of creative expression for others out there. It's worth noting that there was a bunch of reverse engineering work of various files happening all at once. Thus, this account is not precisely historically accurate in order to keep its scope to the topic at hand. Anyway, without further ado, let's get started. While I said we're not going to be talking about the stuff I wrote about in my blog posts, that is sort of a half-truth. In order to explain how I reverse engineered these files, we're going to have to retread some ground I covered in Chokuretsu ROM Hacking Challenges Part 4, Event File Excavation, because that's where I started with the script files. However, this is not going to be a rehash of that blog post. While it focused specifically on covering how I reverse engineered this file for the purpose of translating it, we're going to be focusing on reverse engineering the file completely. In other words, we're not going to just be looking at replacing the dialogue lines. We're going to be trying to get a full understanding of the entire structure of the file. This means that I'm going to be using some different tactics compared to the previous blog post, so while it will start off in a similar place, we'll quickly be diverging. So to start with, as usual, I bought Suzumiya Haruhi no Chokuretsu for the Nintendo DS and then dumped the ROM using my hacked 3DS. Then my friend Ermi sent me a program he and famed hacker Jericom wrote called Nitro Packer, and I unpacked the NDS ROM. Wait, I hear some of you who didn't watch my previous video saying, "What do you mean you unpacked the ROM?" All NDS ROMs have an internal file system called NitroFS. This, in effect, makes them a type of archive, a file which contains other files. NitroPacker, a program that I now maintain, understands the structure of the NDS archive and can extract files from that archive onto disk. This ROM doesn't have a ton of files in it. There's these 2 directories, BGM and VCE, which contain the game's background music and voice files, respectively. There's also this movie directory, which contains 2 mods files. These are the OP and ED videos, or opening and ending, songs, for those of you who aren't weebs. But most importantly, there are 5 bin files in the root directory: dat.bin, evt.bin, grp.bin, scn.bin, and snd.bin. smd.bin turned out to be a common kind of archive used in Nintendo DS games, what's called an SDAT archive, a container file for sound effects. The other four, however, are custom archives, which we call Shade Bin archives, named after their file extension and the developer Shade Incorporated, whose SDK is used in this game. The first things I had to do when working on this were reverse engineer the custom shade compression algorithm and these Shade Bin archives. I document my work on both of these things on my blog, and those blog posts are linked below as I mentioned. From the names of these archives, we can make guesses as to their contents. Dat.bin likely contains data files, grp.bin contains graphics, and evt.bin contains event files. Event is a common term in Japanese games to refer to the story, so these are our scripts. scn.bin probably stands for scene. However, this particular archive seems entirely unused in the game, so we're just going to ignore it. So I wrote code to extract and reinsert the files in these archives. Once we did that, we can start looking at them in more detail. I did some work to figure out what the first file loaded into the game was, and it turns out it's this one, file hex 168 or 360 in the archive. Later I learned that these files all have names, so I found out that this file's name is EV1000S. Put that in your memory bank, we'll be coming back to it. So last time, I talked about familiarizing yourself with the tools of the trade, and we're going to loop back to that today. The main tool we're using is a hex editor. For those of you unfamiliar, a hex editor is a tool that lets you view files in their rawest form, bytes. The hex stands for hexadecimal, the base 16 number system that lets us represent the full range of a byte in just 2 digits. The hex editor I use is imhex, which works on Windows, macOS, and Linux, and has a bunch of features in it that make it very useful for reverse engineering. Unlike my last video, we're going to be using a disassembler today. A disassembler is a tool that takes an executable binary file, a file containing compiled code, and disassembles it. This means that it lets us see the machine code in a more human-readable format, the actual assembly instructions that the computer is executing. The Nintendo DS has 2 processors in it, the main ARM9 processor and the sub ARM7 processor. Thus, Nintendo DS games that aren't DSi enhanced or DSiWare contain 2 executable binaries, ARM9.bin and ARM7.bin. Since ARM7 is the coprocessor, that file usually contains boilerplate code that we don't care about. The primary code is in ARM9.bin, so that's what we'll be disassembling. There are 2 major disassemblers out there, the Interactive Disassembler, or IDA, and Ghidra. IDA is very expensive, while Ghidra is free and open source, so we'll be using Ghidra today. So yeah, it is developed by the NSA, and no, I don't know how to feel about that. Finally, we're also going to be using an emulator with a debugger today. An emulator is a program that can run a game on a system other than the one it was intended to run on. So in this case, we're going to need a Nintendo DS emulator for PC. We also specifically want one with a debugger. This means that it has a feature that lets us step through the game's code. As I mentioned last time, the best one of these at time of recording is Nocache GBA. Thankfully, unlike with Dragon Ball Kai, Nocache can actually run this game, so we'll be able to use it to debug. First of all, I need to answer the question of how I found this file. It's actually simpler than you might think. I searched for the text that you can see in-game. There's a couple of ways to do this. One is to use a hex editor like Crystal Tile 2 or imhex that lets you search the entire ROM pretty easily, and indeed that's what I actually did at first. But we're going to do it a slightly different way. Since we expected the file is going to be in evt.bin, we can search over that archive's extracted files using this tool, bgrep. One thing about Japanese games of this era is that you can generally expect that text will be encoded in an encoding called shift-JIS. And encoding is a way of representing text in bytes. You may be familiar with ASCII, as it's the simplest encoding for the Latin alphabet, or with UTF-8, the universal encoding that's most commonly used nowadays. However, in the 2000s, Unicode was not as widespread, and shift-JIS was by far the most common encoding for Japanese text. So first, we're going to search for some text that we can see in the game. Let's search for this first line here. If we use an online shift-JIS to hex converter, we can type out the Japanese in this line and then get the binary representation of it. The bgrep command to search for that text looks like this, and voila, we have a hit. So now we know, like I said, that this first line is in file number 360 in the archive, EV1000S. So let's open EV1000S in imhex and take a look at it. It is, well, it's quite large. At 7 kilobytes, there's a lot to take in, and it can be overwhelming at first. But as usual, we're just going to start at the top of the file and see what we can figure out. Most files have what's called a header that defines how the computer should read the file. So it's a safe bet that if we start there, we'll be able to figure stuff out too. Something we're going to be looking for here is pointers. A pointer is a value that points to some other piece of data. Pointers come in two flavors, addresses and offsets. An address is the absolute location of data in program memory, while an offset is the relative location of data in the file. Put a pin in that, we'll come back to it later. So looking at these bytes at the top of the file, the first thing I notice is that all of them are 32-bit integers. So how do I know that? Well, it's the spacing between them. You can see that we have 1 or 2 bytes followed by a number of zeros that pads the values to 4 bytes. Each byte is 8 bits, so 4 bytes is 32 bits. A 32-bit integer is a very common type of integer. In fact, it's the main integer for the ARM processor used in the DS, which is a 32-bit architecture. This means that memory addresses are stored as 32-bit integers, which means that some of these values are likely pointers. This makes sense. Headers often contain pointers, as that's how you define where the computer needs to look in the file. A quick aside about how integers work in computers. There's actually 2 ways of encoding a multi-byte integer, little endian and big endian. Little endian means that the little part of the integer, what's called the least significant byte, comes first, while big endian is the opposite. In this case, we can tell just by looking here that these are little endian integers since we can see the zeros at the end. But this also fits our expectations as the DS's ARM architecture is little endian as well. Once we understand that, we can immediately tell that this first value is not a pointer, as hex 1b is 27, which is not divisible by 4. Remember that we're expecting that this file is going to be 4-byte aligned. That being said, it's still the first value in the file, so it's definitely important somehow. So let's keep the number 27 in mind and then proceed. The next integer is hex 1A98. That ends in 8, which means this could be a pointer. So let's go to the offset hex 1A98 in the file. When we do that, we can see that we end up at another section composed of integers toward the end of the file. This first integer ends in 7, so it's not a pointer, but it looks like these next integers are divisible by 4, so they might be pointers as well. And now I have a hunch about this first integer here. If we count up the number of integers in this section that follows, there are 103 of them, and 103 is hex 67, so that's neat. This first number is the number of pointers in the section, which we'll call the end pointer section, just for fun. Since we're making progress on reverse engineering this file already, it's time to start representing it in code. So we'll make a new project, a library project and a CLI, like last time for now. You might have noticed that I'm using a different IDE than last time. This is Writer. Writer is now free for non-commercial use, and it's better than Visual Studio in just about every way.
My source is that I made it
So I've switched over to it. In addition, it's also cross-platform, works on Linux and Mac. We're going to work on the library first. I've put code here to handle the compression, archives, and some helpers for reading binary, as I've already done the work for that. We'll now create a class to represent these files in evt.bin, which we'll name event file. In this class, we're going to put unknown 00 for the first value in the header, and then follow it up with a list of integers to represent the endpointers we found. We can write some constructor code that accepts a byte array, the entire binary contents of the file, and begin parsing this out now. Simply read in unknown 00, then read the pointer that follows it, and loop through the endpointers to have all of those in memory. Nice! The next number is hex E4. This number is also a pointer, and it points to this string here, EV1000. This could be a pointer to the file name, but let's reserve judgment for now. We then have a pattern I notice. The next number is clearly a pointer, followed by 1, not a pointer, followed by another pointer, followed by another 1, which is not a pointer, and so on. If we count how many integers there are here that follow this pattern, we can see that when we reach that string we pointed to before, we have 54 integers. Okay, wait a second. 54 is 27 times 2. And this seems to be a pattern of 2 integers, a pointer and something else we don't understand yet. So this first integer is the number of pointers at the front of the file, and this third integer is actually the length of the header, or the pointer to the start of the file data, which are equivalent. So we'll update our class with that information. At this point, we've figured out some interesting information. I think it's time that we see how some of this data is actually used in this game, so let's introduce our next tools, the disassembler and debugger. Let's open this ROM in Ghidra. Ghidra has a very active community, so there's a bunch of neat extensions for it, including a quite excellent extension for Nintendo DS games. We can install that extension and then load the ROM. We're going to be looking at the ARM9 binary, so we'll select that that's what we want to disassemble. Once we do that, Ghidra will analyze the ROM and output the assembly. Specifically, it will break the game's binary out into subroutines, i.e. individual functions. This is super helpful for analyzing the game's code, as it lets us focus on particular functionality in parts, rather than having to look at everything as a whole. Ghidra also has a built-in decompiler. This lets us see the assembly in C-like code, which is also extremely helpful for analyzing it, as it can be much easier to understand than the raw assembly a lot of the time at least. However, even though we have the ROM broken out into subroutines, we still have no idea where to start, as we don't know which part of the code deals with the files we're looking at. So let's try to figure that out. We'll start by trying to find the file that we're looking at while the game is running. So we're going to open up the emulator Desmume, which has the best memory search functionality of the main emulators. Just change our search options to search for 4-byte hexadecimal, and plug in 4 unique seeming bytes from the file. From prior experience, I recommend not plugging in values that we think are pointers, as frequently those offsets get replaced by addresses at runtime, so we wouldn't be able to find them anyway. So let's boot up the game and go to where this scene starts, which is where the file will be loaded into memory. And we're going to try searching for this value here. As we can see from the Shift.js view, this is dialog that shows up in the first text box, so it's likely unique to this file. And if we search here, we can see we only get 2 hits. Opening up the memory viewer, the first address we have doesn't look quite right, but the second one is right on the money. Scrolling up in the memory viewer, we can find that hex1b that is at the beginning of this file, and we have our file address in memory, 21C4280. So, okay, now that we have this memory address, what are we going to do with it? Well, what we want to do is find code that is operating on this file. So we're going to want to find when something reads from this memory around here. So next, we're going to open up NoCacheGBA and set a read breakpoint for this address. A breakpoint is a function of the emulator's debugger that will stop code execution given a certain condition. In this case, it stops when this address is read from, which is exactly what we want, when code is accessing this address. Doing that and launching into the scene, we immediately hit our breakpoint before the screen even fades back in. Perfect. In this case, it looks like the address we've hit is hex 20261cc. So let's go to that address in Ghidra. At this point, I've already done a lot of work reverse engineering the archives and compression algorithms, so I've already named this function. I've called it arc_decompress to indicate that it's the decompression function for the shade bin archives. Since we don't care about the file being decompressed, we can continue forward with running the program. The next address we ended up at is 2033FD0. This isn't a subroutine I haven't named yet, but it's called right after a routine that I've named arc load file. So this is something that happens immediately after the file is loaded into memory. The instruction we've stopped at is LDR R1 R00. This instruction loads a value from memory into a register. In this case, it loads the value stored at the memory address contained in register R0. Offset by 0, so just that address. In the Nintendo DS's ARM assembly, the return value of the previous function is stored in R0. So in this case, R0 contains the return value of arc load file. If we look in NoCacheGBA, we can see that the value of R0 at this point is hex 21C4280, which is the address of our file we found. That means that arc load file returns the address where it loaded the file in memory. As expected, this is loading that integer hex1b into a variable stored in the register R1. And indeed, after this instruction is executed, we can see it do just that. We can look at the decompilation in Ghidra to get a better understanding of what is happening here. So the first line of the disassembly is what we just described, the program calling arc load file and saving the returned address of that file as an integer array. We'll call this variable event file since it's operating on that. The next thing it does is initialize another variable to 0, and then it checks to see if the first integer in the file is less than 1, and leaves the subroutine if it is. This gives us some hints. It's expecting that the number of front pointers is going to be at least 1. Next, we have a do while loop, so let's analyze what's going on here. Ghidra's decompilation is, well, it can be a little tough to parse sometimes, but we'll do our best here, okay? So the code starts by assigning ivar2 to ivar1 plus 1, which we'll just ignore for a second. The next line is where the magic is happening in this routine. We're indexing to the array of the event file. Specifically, we're looking at the integer at index ivar times 2 plus 3 in the array. Oh! That's actually really neat. That plus 3 indicates that it's skipping the first 3 integers of the file. So it's skipping the number of front pointers, the pointer to the end pointers, and the header length value, and going straight into the front pointers themselves. That times 2 means that it's specifically going to be operating on the pointers rather than the values after them that we didn't understand yet. This is actually really cool. What we're assigning to those pointers is their same value plus the address of the event file. Have you guessed what this is doing yet? I could be one of those educational YouTube channels here where I'm like, okay, take a moment to think and figure out what it is. Like, try to make a guess here or whatever. I don't care. Anyway, keep watching. We can watch this routine play out in the debugger as it modifies the program's memory. What it's doing is looping through those front pointers and converting their offsets to absolute addresses to make accessing the values they point to easier for the program. Kinda neat. So that's the pretty simple function knocked out. Since that's the whole disassembly for this routine, let's name this function arc load file and resolve pointers to indicate what it does. After we leave this routine, the first value isn't read anymore, and the game just continues playing. This makes sense, as it would likely only be used to resolve those pointers when the file is first loaded. So let's go back and see if we can make sense of the pointers we just analyzed. The first pointer we have is hex 1970, and its companion value is 1. If we go to hex 1970 in the file, we can see we end up in a section with a number of other pointers and other values. If we cheat and look later in the header, we can see that a lot of these pointers are contained there as well, so that's quite interesting. I'm not sure what it means yet, but it's another thing to put in our memory banks and return to later. Our next pointer is hex EC, and its companion value is also 1. Jumping there, we can see that it's just 4 0 bytes before we get to the next pointer defined in the header, which is hex F0. So let's ignore it for now. F0's companion value is 2, and we can see that it is 6 integers before we get to hex 108, which is the next pointer in the header. However, this second integer here is interesting. It's hex EC, which is the previous value we had in the header. Yet another thing to put in our hat for later. Hex 108's companion value is 1, but it's just 0 again. However, it's followed by hex 110 companion value 2, which again, the second value is hex 108, a reference back to the previous section. Zooming right along, we have hex 128 companion value 1, just zeros again, followed by hex 134 companion value 2, again with a reference to hex 128. We have the same pattern one more time with hex 14C and 158 before we finally see something different. Hex 170 companion value 3. This one has a bunch of zeros, but eventually we get two values, hex 3E8 and hex 1AC. Both of these could be pointers, but it's worth noting that 3E8 is exactly 1000 in decimal, which is a pretty round number. What's more, it seems to point to a somewhat random data later on, while hex 1AC points to something prior to the next pointer. This string here, which reads Haruhi ni tsuite, or about Haruhi. Okay, that's interesting. I've played through this scene and I know that this text does not show up anywhere, so I'm not totally sure what this is yet. However, I'm starting to notice a pattern here. These front pointers seem to be dividing the file into sections. Each pointer points to the start of a section, so what are the companion values then? So far, we've mostly seen small values, so let's take a look at a section with a larger companion value and see if we can figure it out. We'll take this one here, the section starting at hex 23C, which has a companion value of hex 30. With the exception of the first and last ones, these sections mostly seem to be defined sequentially, so we can assume that this section ends where the next pointer begins, hex BB0. Let's scroll down and take a look. Immediately, we're right in the thick of it with numbers. Hex 2, hex 20C, hex 47C, hex 18, hex 214, hex 49C, hex 02, hex 20C, hex 40. Right away, we can see a pattern. These two values are repeated, and this third value seems to be steadily increasing. Hex 2 doesn't give us much yet, but hex 20C could be a pointer, and indeed, it points to this string here, Haruhi. Okay, we're starting to cook. The next value, hex 47C, points to this string, SOS dan kakigashiku nai niran yo. We've cracked something here. This is the first line of dialogue in this scene. Following along, the next two values are different, but hex 49C points to the second line of dialogue. What's more, that second value points to this string, monoro, which is probably short for monologue, and this line is Kyon's monologue. The line after that is spoken by Haruhi, and those first two values repeat again. These are structures that represent the lines of dialogue, and each one seems to be 3 integers, or 12 bytes, long, with the first two values being related to the speaker and the last being the line itself. So let's back up here. While these dialogue lines are part of this section, they're clearly in a separate data chunk from the structures that reference them. I have a hypothesis right now. There are hex 240 bytes between the start of this section and that first line of dialogue. If we take hex 240 and divide it by the length of each structure, 12, or hex C bytes, we get hex 30. That's the companion number we had for this section. That's way too good to be a coincidence. The companion numbers to the section pointers must define how many items are found in each section. To confirm this, we can look at some other sections. The next section, starting at hex BB0, only has 1 item, but the one that follows it at hex BB4 seems like it would have 9. It should run to hex CF8 based on where that section that follows it starts. So hex CF8 minus hex BB4 is hex 144, which divides evenly by 9 into hex 24, or 36 byte segments. The fact that this section is evenly divisible by 9 is already a great sign, but let's take a look at it to confirm. If we go to hex BB4, we have this hex 2 integer followed by hex B7 and then bunch of zeros and then hex 37. That hex 37 happens to be exactly hex 24 bytes from the start of the section. It then has a single hex 1 following it, and then hex 24 bytes later we have the next number, hex 19. This is really looking good for our sections theory, good enough that we should update the class with this information. We don't know what all of these sections do, but we do know that there's going to be different types of sections. So let's make an interface that defines what all of these sections have in common. Since objects will be of different types, we'll make this interface use a generic type for them. Then we can make these front pointers into a list of iEvent sections with generic objects so we can slot whatever we want into them for now. After that, we can then go back into the constructor and initialize each section with the number of objects it has. Now that we understand that these are sections with discrete items, let's try reanalyzing some of the sections we looked at previously. We'll start with the first section in the list that's at the end of the file right before the end pointers section. It's a single item apparently, and it should go right to where the end pointers start, so we can assume that this section is hex 128 bytes long. As we mentioned previously, it seems to be a structure containing pointers like the header itself, so maybe we can guess that these other numbers are also item counts. We have this first pointer that goes to the title of the script, and then these next few pointers all point to sections with their item counts preceding them. But noticeably, their item counts are 1 less than they are in the header, and looking more deeply, this actually makes sense. If we assume that this section, for example, has 2 items and is 6 integers long, we can guess that it's structured into 3 integer structs. The second struct, however, is null, all zeros. So it's possible that these sections are padded and the header accounts for that padding, but the section down here displays the actual number of items encoded in each section. I'm going to call this the settings section. It lays out the settings for the file as a whole, more precisely defining its sections than the generic header does. At this point, I'm going to introduce a wrinkle. We're going to analyze more than one event file so that we can start comparing and contrasting how they work. This is going to be very useful for checking our work and seeing what we can rely on for parsing them. Let's open up the very next file, number 361 or hex 169, which is called EV1001S. Starting at the top, we can see that this one has a lot more sections than EV1000S. Hex 42 corresponds to 66 sections in total. The settings section, however, is still defined as the first section in the header, so let's jump there and start comparing. We can see here, the title is again the first pointer defined here, followed by the next few sections and their counts. There are some differences, however. This one seems to have more sections defined. Let's also take a look at this section. In EV1000, it had 2 items, while in EV1001, it has 6. Let's jump to it and compare. There are in fact more objects in EV1001's version of this section, and this time I actually recognize what these are. These pointers here point to these strings down here, just like in EV1000, but these strings are actually used. Specifically, they're the text of the options you see when the little choice selector pops up in the game. We can also see that this earlier integer is not a pointer, as it's incrementing by 1 in each object. 1000, 1001, 1002, so on. This is super cool. We are seeing that these sections are neatly defined in the settings section, with each position clearly corresponding to something. This section we just found is the choices section. We're starting to figure out a lot about this settings section, so we should probably create a class to represent it. It will inherit our interface and take an object of a class we'll call event file settings. To define that object, we're going to need to start defining other sections. So far, we've positively identified the dialogue section and the choices section, but we can also take these sections at the top that we don't understand yet and define them as various unknown sections. The first property in the settings is the name of the script file, and then we follow that with a list of sections and their object counts. For now, we'll use the settings section as a repository for the pointers to these sections to make parsing the file easier. We know that the choices section is defined here at hex 3C, and comparing the other pointers, we can see the dialogue section is defined at hex 64. We'll name these other sections that are defined here as unknowns for now. Finally, in both of these files, we have all zeros once we pass hex 7C, so let's just assume that's padding. Now that we've defined the settings section, let's move on to coding up some of the other sections we understand. We'll start with the choices section. We'll define it, again inheriting the interface, and then have it take an object of type choice. We know each choice is 5 integers long. This first one we'll call the ID of the choice, followed by 2 padding integers, the pointer to the text, and then another padding integer. We don't have to store the pointer to the text, since if we modify this file, that pointer will change. So we'll just extract the text from the file directly like so, and store that. The dialog section is very similar. We'll call its objects dialog lines and then define those. We know these dialog line structures are 3 integers in length. The first one is unknown, but the second points to a character. Analyzing these further suggests that this is the name of the character who's speaking. I like to call these sections the dramatis personae sections, so we'll call this the dramatis persona. Finally, we have the text of the dialog line. We can then parse all of these values like so. Before we move on though, let's do a quick bit of analysis on that first unknown value. The simplest thing we can do is to try changing it and see what happens. So let's change this first 2 in the script to a 1 and load the game up and, oh, now it's Kyone saying the line. Well, that was easy. So this first unknown value is actually the thing that controls the speaker of the line. We can do some quick testing by increasing this value by 1 after each dialogue line and get a list of all of the speakers in the game and then put these values in an enum like so. Also, it turns out that these directly correspond to the order of the nameplates in this graphics file I found later, so that makes perfect sense. Next, let's analyze these unknown sections. These first few all have something in common. They contain pointers to other sections. To me, this suggests that these are all potentially lists of sections, even though all of these lists are only 1 section long. So, let's call these pointer sections, since they contain pointers to other sections. While some of the sections they point to have entries, editing those entries doesn't immediately seem to cause any changes when loading up the script, so let's ignore them for now. Next up, we have something similar to what we saw with the choices earlier. If we analyze this value as a 16-bit integer, it comes out to around 2000 in decimal, and this is followed by a pointer to a string, none/cell000. Then we have 1000, 1001, 1002, 2004, and so on, each of these also containing a string, none/cell001, none/cell002, none/cell003, none/celln01, etc. Okay. This is kind of interesting. Similar to the choices, this is an ID and then a label of some kind, but I'm not really sure what it is yet. So that's another thing to keep in mind as we move forward. Let's remember that there are 27 of these in EV1001. After that, it's the dialogue section, which we already figured out, so let's keep going. The next section is a series of pointers to particular strings. Now, these strings are kind of interesting. See how they start with F and have various equality and Boolean operators like AND? These look like conditionals, perhaps values referenced by the script to determine branching logic. We don't know what these are used by yet, but we're going to call this the conditional section for now. The next section referenced by the settings is itself a section of pointers. There are hex 1c, or 28, entries here. If we assume that these last 8 bytes of all zeros are padding, that means that we have hex E0, or 224, bytes of data divided by 28 entries, which gives us 8 bytes per entry. And that sounds about right. There's an integer here followed by a pointer for each one of these entries. If we follow along with the pattern so far, we can assume that these are yet more section pointers and that the first integer is the number of entries per section. Looking at the first one in EV1000, we can recognize that we actually analyzed it earlier. This is a section with hex 24-byte entries. Now that we've recognized these sections, we can look at them more closely. Each entry seems to be composed of an initial integer followed by a series of 16 shorts. I have an inkling of what these might be, but I'm going to keep it a secret for the dramatic reveal. So let's say we don't know exactly what these do. The easiest thing to do, then, is to let the game teach us. It's time to go back to the debugger and the disassembler. Let's use the memory addresses we found earlier and set a breakpoint at this value, hex 02. In no cache, we can set a memory read breakpoint there just like before and load the scene, and we have a hit, hex 20513AC. Time to take a look in Ghidra. Here's where the magic happens. When we go to that instruction, we can follow it through Ghidra's decompilation as well. On this line, that first integer is getting loaded into a variable. Skipping down a couple of lines, we have a constant pointer being loaded into this variable. These two combine here to make a dynamic call to a function, meaning that the static variable being loaded in is a table of functions. If we go to it, we can see that, indeed, each of these pointers points to a specific function. So what have we found here? This is a table of commands, and we've stepped directly into the script execution engine. This is incredible because we found the heart of what makes these scripts tick. If we can figure out what all of these commands do, we could probably create a script from scratch and take our first monumental step on that road to being able to remake the game like I did in that video. So, let's get started, shall we? We now know that the first integer we see here is the command ID, so we can surmise that the next 16 shorts must be the parameters for each command. But we should test this, which also leads us to our first way of reverse engineering a scripting language. Changing parameters. Let's take this first command ID, hex02. It appears in both of the scripts we've been looking at, and it has the same parameter in both as well, hex B7. Why don't we try changing hex B7 by 1 to hex B8, just for fun? Loading up the first script, it doesn't look like much changed, but when we go into the second, we can quickly see that the top screen background is different. From exploring the files, I know that these backgrounds are labeled KBG. I've been calling them kinetic backgrounds. I don't actually know if that's what they stand for, but you know, it's fine. So I'm going to name command 02 KBG disp, for KBG display, to be clear. Let's do a couple more for fun. The next one here is hex 37. Let's try changing this 1 to a 2. Loading back into this scene, we can see that the episode header at the top has changed to show episode 2 now. We can mark this command as epheader. In our other file, the second command is hex B. Changing this 1 to a 2 like before and loading back up gives us different background music. So this command can be called BGM play. Skipping over the second parameter, the third is 100, which sure sounds like it might be the volume of the background music. If we change it to 50 and load back up, sure enough, the volume has decreased. Ad hoc testing will only get us so far though. Changing the second parameter's 2 here to a 3 makes it so the background music doesn't play at all, but that doesn't tell us much about what this parameter is doing. Let's build something that will allow us to more easily compare these commands. I'm going to modify the Haruhi Chokuretsu CLI that I built for translating the game in previous blog posts to allow us to search for commands and even filter by parameters. This way we can see what other valid values are for these commands and figure out what they do. So for example, if we change this later BGM play to have 04 for the second parameter, as we can see some other commands do here, we can see that it stops the background music. This parameter determines whether to start, 2, or stop, 4, the background music. Let's skip ahead a bit and take a look at 4 commands I want to show you because I know they'll be instructive. Here we have hex 18 followed by 2 zeros and then hex 7d6, or 2006 in decimal. Then we have another hex 18, this time followed by a 1 and then a 0, and then hex 77, or 2007. We then have hex 19 followed by a 0 and then hex FFFC, which is -4, and then a hex 13 command with a single hex 78, or 2008. These values, which coincidentally correspond to the years immediately following the release of the first season of The Melancholy of Haruhi Suzumiya, seem pretty unique, so let's try searching for them. When we do, we end up back in that section that we said we'd come back to earlier with the none strings. If we look for the values 2006, 2007, and 2008, they correspond to the strings none/HM100, none/HM200, and none/HM300. That's interesting, I guess, but what does it mean? Well, now that we know that it's referencing values from this section, let's try changing these 3 values to others in this section. We'll pick none CP000, none CP100, and none CP001, just for fun. Loading that scene in the game back up, we play for a bit and then something odd happens. We suddenly are in a completely different part of the scene. This interaction happens much later when you talk to the Computer Society members. Take a guess as to what's happened here. What we've just found are commands that affect control flow, i.e. the order in which commands are executed. The section with the labels has 27 elements, as we noted before, and there are 28 script sections. These are labels for, or the names of, all of the script sections after the first one. Command hex 13 is go to. It jumps to a specified script section. The two hex 18s are V-go-tos that jump to a particular section if a particular condition is met. The first parameter is actually an index into the conditional section that we found earlier. Hex 19 isn't control flow, but if you're curious, it controls the Haruhi meter. Yes, this game has a Haruhi meter. So these sections labeled HM that we were just in are named that way because they all have different possible modifications to the Haruhi meter. So far, we've made great progress with reverse engineering these commands just by modifying the values in the script. However, what happens when we come across a command that doesn't seem to have any effect? For example, changing the values in this hex D command doesn't seem to do much at first blush, and looking at other scripts shows that it's used a lot, but not much else. However, because we have that table of commands in the disassembly, we know exactly which subroutine this command calls. So let's go look at the decomp for it. We can see here that it checks the second parameter. If that parameter is 0, it calls a function with the first parameter as an argument, and if it's 1, it calls a different one with that same argument. Let's open these functions up and take a look at them. Now, these look complicated at first, but they're really not so bad once you take a closer look and contrast them. Specifically, look at these bitwise operators. In the first one, we're bitwise ANDing with the bitwise inverse of some values, and in the second one, we're bitwise ORing with the values as is. These are the signatures of flipping a specific bit to 0 and 1 respectively, i.e. we're looking at a command that does flag manipulation. Let's name this first function EVT clear flag and the second EVT set flag, and we'll call this command flag. This technique of looking at the disassembly is so powerful that I even used it to do something that I think is very special. Command hex20 isn't used anywhere in the game, but it does have a subroutine associated with it. By looking at the disassembly and the decomp, I was able to figure out what the valid parameters were for this command and reconstruct it whole cloth. It turns out it displays the entirely unused items in the game, so I named it item disp image. Repeat this process over and over again, painstakingly delving into each subroutine for each command, and eventually you end up with something like this. This is my documentation for the Chokuretsu scripting engine. All 45 commands are documented here. But we're not done yet. Take a look at this slot. Hex 9 is a removed command with no subroutine associated with it. Seems a shame to have unused space there. What if we filled it with something else? I'm going to be glossing over a lot of information here for the sake of time, but suffice it to say that these chibi sprites you see on the top screen have a lot of different animations, some entirely unused, and have room for even more. What if we wanted to play some of these animations on the top screen? I ended up combing through the code I found as a result of reverse engineering the scripting language, and found the spots that controlled which animation was playing for each chibi on the top screen. Then I wrote some C code and some quick assembly to inject into the ROM, including making sure that we inject our new subroutine into that table of commands that we saw before. After that, I modified a script file to contain a reference to my new command, and we've just written our own command for this scripting engine. Look at my girl, watch her run. She's so good at, she's running. I love her. She's so good at running. Oh my gosh, watch her go. Wow. Editing these files this way is difficult though, so the next step is to grab a friend who's good at GUI work, thank you William, and get to work creating an editor for the game. On the screen right now, you're seeing a development time-lapse of the last few years of serial loops. Here's the part where we got to developing the script editor, implementing each command and making it so you could preview what the result in the game would look like as you edited. Here, we completely redid our interface, and most recently, I added animated script previews to the editor. Making an editor like this is a labor of love, and my way of giving back to the community, I guess, the fandom. I don't know exactly who's benefiting from this, honestly, but I hope that it brings someone even a fraction of the joy it's brought me in creating it. There's a lot of other features packed into the tool, allowing you to edit most parts of the game. If you're interested in telling your own stories in the Haruhi universe, I hope that you'll give Serial Loops a shot and send any feedback or requests my way. Before I close out, I'd like to note that if you found any of this interesting, I'll be doing a panel at SakuraCon in Seattle on Sunday, April 20th at 10 a.m. in Ballroom 2. They upgraded me to one of the largest rooms, and it's a 10 a.m. panel on a Sunday. Please come so I don't end up like these girls in Zombieland Saga at the beginning of Revenge when they go to like the Saga Stadium. You know what I'm talking about? I'm going to put a clip on the screen. You'll know what I'm talking about. Alright, well, that's all for me this time. Please leave any thoughts you have on the video in the comments below. This is only my second video of this sort, and I'm eager to improve as always. Thanks for watching.